Ready.
Hi everyone, I'm Stephen Capasso. We're going to do problem 1 from homework 6. This problem has to do with two functions of two random variables. We're giving a joint density function, fx of y, 1 plus xy over a, and some ranges. Absolute value of x is less than 1, absolute value of y is less than 1. 0 elsewhere. I think it's important to note that when you're giving this range information, right there it gives you significant information about your integration ranges. For instance, for x it's going to be from -1 to 1, and y it's going to be -1 to 1. I think it's always good to look into those ranges to get your integration range information. Now, this first part of this problem is we have to find a such that the density function, the joint density function, is a valid joint density function. And we do that by integrating and setting it equal to 1. And then solving for a. And upon doing that, here I get a is equal to 4. I think that should be 2, based on one of the solutions to another homework, but I got 4, so I'm leaving it like that until I see otherwise. Now I'm going to the next part. Part 2, we're asked if x and y are uncorrelated. I'm saying that no, they're not. Why? Because the correlation coefficient rho, is it equal to 0? That's really what we're asking here. And what we see from the density function is that we have 1 plus xy over 4. We could solve for x and we could solve for y. But and more importantly, since x and y are multiplied together, they must be correlated. So the answer to the question is no. Now, are they independent? Are x and y independent? So we have this expression where we compare the overall joint density function to the multiplication of the two individual density functions. And doing that, we see that they are not equal, so therefore x and y are not independent. That's that. The last part is finding the joint density of, as it reads, x squared and y squared. We're not really talking about x squared and y squared. This means the second moment of x and the second moment of y. So this is a moment problem, and there's some notation in the book. Page 214 actually really does a nice job of defining this, and we have this factor little m, case of r, and it leads to the fact that little m20 is what we want. That's the expected value of x, second moment of x, right? And same with y. It's m02, so the second moment of y. Now, if we evaluate the second moment of x, we end up with this integration formula. And going through it, we end up with second moment of expected value of x is 1/3. And then we do the same for the second moment of expected value of the second moment of y, and we end up with the expected value for the second moment of y is 0. So finally, prove or disprove that x squared and y squared are independent, or second moment of x and the second moment of y are independent. So I'm going to say that we prove this by the density function of x times the density function of y. Is that equal to the joint density function? And or actually, assuming that the joint density function of x squared, y squared, second moment level, is not 0, we can find that we have this quantity, fx of x times fy of y, is not equal to the overall second moment density function. So therefore x squared, y squared are not independent, or the second moment's levels are not independent. That's it.